January 31st, 1958, Cape Canaveral, Florida. Dr. James Van Allen stood in the cramped blockhouse, watching through reinforced glass as the modified Jupiter C rocket sat on the pad under floodlights, white vapor bleeding from its liquid oxygen tanks into the cold Atlantic night. The physicist from the University of Iowa had not slept properly in 4 days. His instruments, 2 Geiger-Müller tubes and 1 cosmic ray detector, packed into an 18-pound cylindrical payload at the rocket's nose, represented 8 years of theoretical work, 3 years of engineering refinement, and the last chance for American credibility after 2 humiliating months. He could still hear the laughter. Not from this room, but from the international physics conferences, from the Soviet Academy of Sciences publications, from Radio Moscow broadcasts that his colleagues had translated for him. When Sputnik 1 had crossed American airspace on October 4, 1957, Soviet engineers had made their position clear. American satellite plans were primitive fantasies, delayed by bureaucratic incompetence and technological inadequacy. When Sputnik 2 launched a month later, carrying the dog Laika in a capsule weighing 1,120 pounds, 6 times heavier than America's proposed satellite, the message became louder. The United States had announced satellite intentions in 1955. The Soviet Union had launched 2 operational spacecraft before America could orbit a single pound of metal. Van Allen pressed his hand against the concrete wall. The blockhouse smelled of cigarette smoke, electrical ozone, and human anxiety. Around him, 37 engineers and officers monitored consoles displaying fuel pressures, guidance alignment, tracking radar status. Lieutenant John Meisenheimer, the Army Ballistic Missile Agency launch director, stood beside the firing console, watching the clock. Wernher von Braun, the German rocket engineer whose team had built this missile, sat in the back row, his face unreadable. Von Braun's modified Jupiter C, officially designated Juno 1, had been ready for satellite launch since September 1956, but the Eisenhower administration had insisted on waiting for the Navy's Vanguard program. Political optics, civilian achievement, international prestige. All of it irrelevant, now that Vanguard TV3 had exploded 4 feet off the launch pad on December 6, 1957, while live television cameras broadcast the fireball to 78 million Americans. The countdown reached T-minus 60 seconds. Van Allen thought about the cosmic ray data he expected to collect. High-altitude radiation measurements, solar particle interactions, standard magnetospheric research, the kind that might earn him another grant and perhaps a journal publication. Nothing revolutionary. Just good science if the rocket didn't explode. But the instruments contained a modification he had made 3 weeks earlier, based on an anomaly he'd noticed in V2 rocket data from 19. At certain altitudes, radiation counts had spiked beyond anything solar flares could explain. He'd added a backup Geiger tube with a different sensitivity range, just in case. It probably wouldn't matter. But space was the one environment where Earth's magnetic field extended into regions humans had never measured. And Van Allen had learned not to trust assumptions about unmeasured territory. 10 seconds, Meisenheimer announced. The turbopumps ignited. 78,000 pounds of thrust erupted from the Rocketdyne engine. The Jupiter C rose on a column of white fire, accelerating through 60 miles per hour before it cleared the tower. Van Allen watched it arc eastward over the Atlantic. The engine glow shrinking to an orange point, then vanishing. The tracking radar maintained lock. The telemetry signal stayed clean. First stage burnout occurred at 1:05. The solid fuel upper stages, 11 clustered Sergeant rockets rotating inside a spinning tub, ignited in sequence, each burn adding velocity. By the time the final stage cut off at 510 seconds, Explorer 1 was traveling 18,000 miles per hour. At 12:54 a.m., February 1, 1958, tracking stations in California confirmed orbital insertion. The United States had a satellite in space, 84 days after Sputnik 1. Van Allen felt no triumph, only exhaustion and the beginning of data collection. The real work started now. He did not know that the instruments spinning over his head, in an elliptical orbit ranging from 220 miles to 1,563 miles altitude, were about to record readings that would invalidate 60 years of assumptions about Earth's magnetic environment. He did not know that within 4 months he would present evidence of radiation zones so intense they would reshape every plan for human spaceflight. And he did not know that the Soviet engineers who had laughed at American delays were, at this same moment, analyzing Sputnik 2's radiation data and finding measurements that made no physical sense, measurements their instruments were too crude to interpret, measurements that matched exactly what Van Allen's more sensitive detectors were about to reveal with perfect clarity. The discovery would not announce itself with drama. It would arrive as a blank spot in a data stream, a silence where numbers should have been, an absence that meant the instruments had encountered something so far beyond their design parameters that they had stopped counting entirely. The laughter had started in Moscow. At a reception in the Hall of Columns on October 12th, Dr. Anatoly Blagonravov, the Soviet space program's public face, stood before 200 international journalists and described Sputnik 1's successful operation with the measured confidence of a man who understood he had just humiliated his rivals. The satellite, he explained, had transmitted temperature and pressure data on every pass over Soviet tracking stations. Its radio beacon had operated continuously for 22 days before battery depletion. The launch vehicle, a modified R-7 intercontinental ballistic missile, had delivered 184 pounds into a stable orbit. The telemetry was clean, the trajectory was predictable, the engineering was complete. A British journalist asked about American satellite plans. Blagonravov allowed himself a diplomatic smile. "We have read their announcements," he said. "The Vanguard program is very ambitious. Perhaps in 1959 or 1960 they will achieve success." The room understood the implication. Project Vanguard, announced by President Eisenhower in July 1955 as the United States' contribution to the International Geophysical Year, had promised a 3.25-pound satellite by late 19. That deadline had passed. The rocket existed only in test configurations. The Navy's insistence on developing entirely new technology, a new launch vehicle, new guidance systems, new tracking networks had produced delays, budget overruns, and now international embarrassment. The Soviet Union had used a military missile, accepted the engineering compromises that required, and won. But the technical reality beneath the propaganda was more complicated than either side acknowledged. Sputnik 1 was a magnificent achievement in orbital mechanics and industrial coordination. The R-7 rocket represented a genuine breakthrough in thrust and staging. But the satellite itself was a hollow sphere containing a radio transmitter, thermal switches and batteries, instrumentation any competent engineering team could assemble. It had proven the Soviet Union could reach orbital velocity. It had not proven they understood what existed in that environment. The Soviet scientific community's attitude towards space radiation research in 1957 reflected a theoretical confidence that Western physicists found troubling. Soviet papers on magnetospheric physics, translated and analyzed by the CIA's Directorate of Science and Technology, consistently described Earth's radiation environment as extending no more than 50 miles altitude, tapering smoothly beyond that point until solar particles dominated at geosynchronous distances. This model, developed by Soviet Academy of Sciences researchers using data from high-altitude balloon flights and theoretical calculations, had become scientific consensus in Moscow. It was elegant, mathematically consistent, and completely wrong. American understanding wasn't significantly better. Dr. James Van Allen had spent the previous 8 years launching instruments on V-2 rockets captured from Germany, on Aerobee-sounding rockets, and on the Navy's Skyhook balloons, platforms that reached altitudes between 20 and 60 miles. His cosmic ray data showed expected results: steady background radiation from solar sources, occasional spikes from solar flares, a predictable decline in atmospheric shielding as altitude increased. He had published 17 papers on the subject. He had received the National Science Foundation's senior postdoctoral fellowship. His understanding of high-altitude radiation was considered definitive, but he'd never measured anything above 60 miles altitude. No one had. The space between the atmosphere's upper boundary and the lowest sustainable orbit, the region from 60 miles to 200 miles, was a measurement gap, a blank zone in the data, where extrapolation replaced observation. Van Allen assumed the radiation environment would behave predictably in that gap. He assumed Earth's magnetic field would deflect solar particles in ways that produced smooth, calculable fluxes. He assumed his instruments would record modest increases in radiation intensity, nothing unusual, nothing that would require theoretical revision. Every one of those assumptions was wrong, but the wrongness would only become apparent when sustained orbital measurements accumulated enough data to reveal the pattern. Sputnik 2, launched November 3, 1957, carried radiation detectors as secondary instruments. The primary payload was Laika, the dog, monitored by sensors measuring heart rate, respiration, and temperature, a demonstration that living organisms could survive launch acceleration and orbital weightlessness. The radiation instruments were Soviet-designed Geiger counters, less sensitive than Van Allen's American designs, calibrated for the expected environment based on Moscow's theoretical models. The readings they transmitted made no sense. At altitudes between 600 and 900 miles, the counters occasionally flatlined, recording zero radiation, physically impossible in any orbital environment. At other points in the same orbit, they spiked beyond calibration range, then returned to normal. Soviet analysts initially suspected instrument malfunction. The electronics were functioning, the power supply was stable, the telemetry was clean. But the data was inconsistent with every model the Academy of Sciences had published. Officially, the readings were classified as anomalous and filed for further study. Unofficially, senior researchers suspected they'd encountered a measurement artifact, an instrument design flaw that would require correction in future satellites. They had not encountered an artifact. They had measured the outer edges of the inner Van Allen belt, a zone of magnetically trapped protons and electrons circling Earth in a toroidal formation, invisible to optical observation, undetectable by ground-based instruments, present since Earth's magnetic field formed billions of years earlier. But their instruments lacked the sensitivity range to resolve the measurements into coherent data. They'd found evidence of the phenomenon but couldn't interpret it. Van Allen's instruments, by contrast, had been designed with a different philosophy. His Geiger-Müller tubes used thin mica windows that responded to lower energy particles, giving them broader sensitivity. His cosmic ray detector, a scintillation counter using sodium iodide crystals, could measure particle flux across 4 orders of magnitude. And he'd included the backup tube with the modified range, the one based on those V2 anomalies from 1952. It was over-engineering, probably unnecessary, the kind of redundancy that added weight and complexity, but Van Allen had learned his caution at the Naval Research Laboratory during World War II, developing proximity fuses for anti-aircraft shells, weapons that had to work perfectly on the first attempt, in environments no one had fully tested. You built in margins. You prepared for the unknown. The unknown was about to announce itself with absolute clarity. February 1, 1958. Goldstone Tracking Station, California. 2:17 a.m. Pacific Standard Time. William Pickering, director of the Jet Propulsion Laboratory, stood in the Goldstone control room, watching the telemetry screens as Explorer 1 completed its first full orbit. The satellite had passed over California 11 times since launch, each pass providing 90 seconds of radio contact. The transmitter was functioning. The temperature data looked normal. The satellite's external shell fluctuated between -40 and +40 degrees Fahrenheit as it cycled between sunlight and shadow, exactly as predicted. The spin rate was stable at 750 revolutions per minute, keeping the cylindrical body oriented correctly, everything nominal. The cosmic ray data, however, was transmitting only intermittently. Van Allen's instruments sent their measurements as audio tones, different frequencies representing different particle count rates. During 8 of the 11 passes, the tones played continuously, rising and falling as Explorer 1 climbed through different altitudes. But during 3 passes at the highest points in the elliptical orbit, the audio simply stopped. No tones, no counts, just carrier signal and telemetry, indicating the instruments were receiving power but recording nothing. The engineering team initially suspected a wiring fault. Pickering ordered diagnostic checks on the receiving equipment. All stations Goldstone, the backup station at Manchester, and the mobile unit at Earthquake Valley reported identical results. The transmission gap was real. At orbital altitudes above 1,200 miles, Van Allen's cosmic ray detector was recording 0 particles. "That can't be right," Pickering said. He'd worked with Van Allen on previous balloon flights. The instruments were proven designs. They didn't simply fail at high altitude. Pull the calibration data, compare it against the V2 flights. The comparison took 6 hours, the data arriving by teletype from Iowa City, where Van Allen's graduate students maintained his research files. The low-altitude measurements matched perfectly. Below 500 miles, Explorer 1's particle counts corresponded exactly to what previous rocket flights had measured. Background cosmic rays, occasional solar particles, a smooth increase with altitude as atmospheric shielding decreased. Above 500 miles, the data continued smoothly upward until suddenly, at approximately 1,200 miles altitude, the count rate dropped to 0. Not a gradual decline, an abrupt cutoff, as if someone had switched off the radiation source. At 9:45 a.m. Eastern Time, Van Allen received the telemetry summary by telephone in his University of Iowa office. He listened to the description twice, asked 3 clarifying questions, then sat in silence for nearly 2 minutes while the JPL engineer waited on the line. "The instruments are saturating," Van Allen said finally. "They're not reading 0. They're reading off scale. The particle flux is so intense it's overwhelming the Geiger tubes. They're encountering count rates beyond anything we designed them to measure." The engineer started to object. The instruments had been calibrated for the maximum expected environment, including severe solar storm conditions, then stopped. Van Allen was right. A Geiger-Müller tube has a characteristic called dead time, a brief period after each particle detection when the tube cannot register another count. At low radiation levels, dead time is negligible. At extremely high levels, when particles arrive faster than the tube can reset, the counts overlap and the instrument effectively goes blind, recording an apparent drop in radiation that actually represents saturation. "How intense?" the engineer asked. "I don't know," Van Allen said. "We'll need to reprocess the data using the saturation curves." But if I'm right, we're looking at radiation levels thousands of times higher than anything we've measured before, thousands of times higher than should exist anywhere in near-Earth space according to current models. He was underselling it. When his team completed the reprocessing 3 weeks later, using the saturation characteristics documented during instrument testing, they would calculate peak particle fluxes of 35,000 counts per second, 40 times higher than the instrument's design maximum. The radiation environment at 1,200 to 500 miles altitude was not a smooth extrapolation from lower altitudes. It was a region of magnetically trapped particles, circulating in Earth's field with intensities that made the surface environment look like empty vacuum by comparison. Explorer 1 had discovered the inner Van Allen belt. March 26, 1958. Washington, D.C., National Academy of Sciences headquarters. Van Allen presented his preliminary findings to a closed session of the International Geophysical Year Satellite Committee, attended by 43 American and European scientists. He'd spent the previous 8 weeks refining the data analysis, confirming the saturation interpretation, and developing a theoretical model that could explain the observations. The presentation lasted 90 minutes. He used no speculation, no dramatic language, just data, graphs, and mathematical analysis. Explorer 1 had detected 2 distinct radiation zones. The inner zone, centered at approximately 2,000 miles altitude, contained primarily high-energy protons trapped in Earth's magnetic field. The outer zone, whose existence Van Allen inferred from gaps in the data, appeared to extend from 8,000 to 12,000 miles altitude, and likely contained trapped electrons. The intensity in the inner zone exceeded 30,000 particles per second per square centimeter, radiation levels that would deliver a lethal dose to an unprotected human in approximately 2 hours. The zones formed toroidal belts around Earth's magnetic equator, thinning near the poles where magnetic field lines allowed particles to escape into the atmosphere, creating the aurora borealis. The discovery invalidated every existing model of near-Earth space radiation. It meant that orbital flight trajectories would need to account for radiation exposure. It meant that instruments designed for space research would need far greater sensitivity ranges. It meant that any plans for human spaceflight, plans both the United States and Soviet Union were developing in absolute secrecy, would need to consider radiation shielding that no one had previously imagined necessary. Dr. Lloyd Berkner, a physicist who had helped establish the International Geophysical Year research agenda, asked the obvious question: how did we not know this existed? Van Allen explained the measurement gap. Ground-based observation cannot detect trapped particles. Balloon flights reached only 60 miles altitude, far below the belts. Sounding rockets traveled vertically through the zones too quickly to accumulate sustained data, and their telemetry systems had insufficient sensitivity. Only a satellite, orbiting repeatedly through the same regions, carrying instruments specifically designed for particle detection, could reveal the phenomenon. The Soviets must have seen this, Berkner said. Sputnik 2 had radiation detectors. Their instruments were less sensitive, Van Allen replied. If they saw anything, they probably interpreted it as instrument malfunction. Our data is unambiguous, because we can track the saturation curves. Without that analysis technique, the readings just looked like noise. The political implications were immediate. The United States had launched its first satellite 3 months after the Soviet Union, but American science had made the first major discovery in space physics. The discovery was not a weapon, not a military advantage, not a propaganda victory. It was simply superior instrumentation deployed with proper scientific methodology. But in the context of Cold War prestige, superior science was superior capability, and superior capability was strategic advantage. President Eisenhower's press secretary announced the discovery on May 1, 1958, at a White House science briefing. The radiation belts were officially named the Van Allen belts 3 months later, after the International Astronomical Union's Nomenclature Committee convened to establish standard terminology. By August, Van Allen had received 14 requests for instrument specifications from international space programs, including 3 requests from European scientists who worked with Soviet contacts. The Soviet Academy of Sciences published its official response on June 8, 1958, in Pravda. The article acknowledged that Soviet instruments had detected radiation anomalies, but stated that American analysis techniques had provided useful clarification of the phenomenon. The phrasing was careful, diplomatic, and entirely inadequate to mask the institutional shock within the Soviet scientific establishment. They had possessed the data first, they had failed to interpret it, their theoretical models had been wrong, and the United States had revealed a fundamental property of near-Earth space that Soviet engineers were now scrambling to incorporate into every spacecraft design. June 15, 1958, Kaliningrad, Soviet Union, Special Design Bureau OKB-1. Sergei Korolev, the chief designer of the Soviet space program, sat in his office reviewing radiation shielding calculations for the Vostok spacecraft, the capsule that would carry the first Soviet cosmonaut into orbit, planned for 1960 or early 1961. The calculations had changed 3 times in the past month, each revision increasing the required shielding mass as the Academy's radiation experts refined their understanding of the Van Allen belt's intensity. Korolev was an engineer, not a physicist. He understood stress loads, propulsion efficiency, guidance systems. He'd built the R-7 rocket that launched Sputnik. He'd convinced Khrushchev to fund the space program by emphasizing its propaganda value in military applications. He'd successfully orbited 2 satellites while the Americans struggled with exploding test vehicles. Now he was looking at American research papers explaining that the orbital environment contained radiation zones his engineers had measured but not understood, zones that would require adding 200 kilograms of lead shielding to a spacecraft already at the edge of the R-7's payload capacity. The Americans had not simply launched a satellite, they had deployed better instruments, applied better analysis, and revealed information that changed every technical requirement for human spaceflight. The discovery demonstrated exactly what Korolev had warned his superiors about for years, that American scientific infrastructure, the university research programs, the instrumentation development, the systematic peer review, produced a quality of knowledge that Soviet centralized planning struggled to match. His design team was competent. The Academy's physicists were brilliant theorists. But the United States had distributed its space research across multiple institutions, JPL, the Naval Research Laboratory, university partnerships, creating redundancy and specialization that Soviet single directorate management couldn't replicate. Van Allen had been free to develop instruments over 8 years, testing iterations on different platforms, refining sensitivity ranges without bureaucratic approval chains. Soviet instrument designers worked under production quotas and schedule pressures that prioritized meeting launch deadlines over exploring measurement edge cases. The result was that Korolev now had to redesign Vostok's radiation shielding based on American data, because Soviet instruments had been too crude to provide equivalent measurements. The political officers would frame this as international scientific cooperation. Korolev understood it as capability shortfall. He picked up the telephone and called Dr. Mstislav Keldysh, the Academy's lead theorist on orbital mechanics. The Vostok trajectory, Korolev said. We need to optimize it to minimize time in the high radiation zone. How much delta V cost? We're modeling it now, Keldysh said. If we keep the orbit below 200 kilometers and above 180, we stay beneath the inner belt entirely. But that increases atmospheric drag. The orbit will decay faster. Mission duration drops from 8 days to perhaps 12 orbits. How many orbits do we need to prove a human can survive spaceflight? 1 would be sufficient, technically. But the Americans will orbit longer once they begin flights. If we want priority, we need duration. Korolev considered, priority meant first, duration meant superior. The Americans had already taken one victory, the scientific discovery. The Soviet Union needed the operational achievement. Plan for a single orbit mission, he said. Maximum altitude 230 kilometers. Minimize radiation exposure. We launch as soon as the capsule is ready. The decision would define the Soviet approach to early human spaceflight. Fast, minimal, first. Yuri Gagarin would orbit once on April 12, 1961, spending 108 minutes in space before re-entry. Alan Shepard would fly a suborbital trajectory 17 days later. John Glenn would orbit 3 times on February 20, 1962. The Americans would eventually achieve longer duration, more extensive research and superior systems reliability. But the Soviet Union would be first, because Korolev understood that in the Cold War's technological competition, symbolic achievements mattered as much as substantive capability. The Van Allen belt's discovery had taught both sides a lesson. The Americans learned that scientific instrumentation superiority could produce strategic intelligence advantages. The Soviets learned that achieving firsts in space required accepting narrower margins and shorter missions. Both lessons would shape the space race's next decade. July 26, 1958. Cape Canaveral, Florida. Explorer 4 sat on the launch pad, waiting for weather clearance. Van Allen had designed this satellite specifically to map the radiation belts with higher precision. The instrument payload had been doubled, 4 Geiger tubes, 2 scintillation counters, a magnetic field detector. The orbital parameters had been optimized for maximum coverage of the high radiation zones. The Juno 1 rocket stood ready. The launch team was in position. And Van Allen, standing in the same blockhouse where he'd watched Explorer 1 leave Earth 6 months earlier, felt the same exhaustion and anticipation. Explorer 4 launched at 12:26 p.m. and reached a stable orbit, ranging from 163 miles to 1,373 miles altitude. The instruments activated. The data began transmitting. And this time, Van Allen's team was ready to interpret every measurement. The second satellite confirmed everything Explorer 1 had revealed and added precision to the boundaries. The inner radiation belt extended from approximately 600 miles to 3,700 miles altitude, with peak intensity at 2,000 miles. The trapped particles were primarily protons with energies above 30 million electron volts, high enough to penetrate several millimeters of aluminum. The belt's shape followed Earth's magnetic field lines, dipping lower at the poles and extending farther from Earth's surface at the equator. The intensity varied with solar activity, increasing during solar storms as additional particles were injected into the magnetosphere. Explorer 4 also detected the outer belt's inner boundary at approximately 8,000 miles altitude. The full mapping would require additional satellites in higher orbits, but the phenomenon's existence was now undeniable. Earth was surrounded by invisible radiation zones that had existed, unmeasured and unsuspected, throughout human history. The discovery reshaped scientific understanding of planetary magnetic fields. Researchers realized that any planet with a magnetic field and an atmosphere would likely trap charged particles in similar belts. Jupiter's radiation environment, measured decades later by the Pioneer and Voyager spacecraft, would prove to be thousands of times more intense than Earth's, a finding that validated the theoretical framework Van Allen's data had established. The belts became a standard consideration in planetary science, a phenomenon that influenced atmospheric evolution, auroral activity, and the distribution of water in planetary systems. But in 1958, the practical impact was simpler and more immediate. The United States had demonstrated that its scientific infrastructure could produce discoveries from the same data other nations possessed but couldn't properly analyze. That demonstration had consequences beyond physics journals. November 3, 1958. Moscow, Central Committee Presidium meeting. Premier Nikita Khrushchev reviewed the classified technical report from the Academy of Sciences on American satellite achievements. The report had been requested after U.S. officials announced that Explorer 3, launched March 26, 1958, had confirmed the Van Allen belt's discovery, and that Explorer 4 had provided detailed mapping of radiation intensities. The American satellite program, which had begun with humiliating delays and an exploding rocket on live television, had produced 3 successful orbital missions in 9 months, each carrying instruments that revealed information Soviet scientists had missed. The report's conclusion was direct. American instrumentation technology currently exceeded Soviet capabilities in sensitivity, reliability, and data transmission quality. The gap was not insurmountable. Soviet engineers understood the design principles, but closing it would require institutional changes in how instruments were developed, tested, and deployed. Khrushchev understood the political dimension immediately. The space race was not primarily about science. It was about demonstrating system superiority. Sputnik had shown the Soviet Union could reach orbit first. The Van Allen belt's discovery showed the United States could extract more knowledge from orbit once achieved. Both achievements were propaganda victories, but they advertised different strengths. Soviet propaganda emphasized bold action and rapid deployment. American propaganda emphasized systematic research and scientific depth. The question was which strength mattered more in the long term. Khrushchev believed correctly that bold achievements captured international attention more effectively than incremental research. The first satellite, the first animal in orbit, the first human in space, these were milestones that non-technical audiences could understand. The discovery of radiation belts was important to scientists but meant little to the average Soviet citizen or neutral observer in the developing world. But within the technical community, within the global network of scientists and engineers whose opinions shaped government policy in every industrialized nation, the American achievement had shifted perceptions. Soviet science was no longer seen as automatically superior. American institutions were producing results that Soviet institutions had missed, and that shift in perception would influence technical cooperation agreements, graduate student exchanges, and the flow of scientific talent, all of which had strategic implications extending far beyond satellite orbits. The Presidium authorized increased funding for Soviet instrument development programs and established a new review process requiring Academy validation of all scientific payloads before launch. The changes came too late to affect the next generation of spacecraft already in development, but they represented an acknowledgement that scientific capability gaps had real consequences. January 2, 1959, University of Iowa Physics Department. Van Allen sat in his office, reading congratulatory letters from colleagues around the world. The Van Allen belts had become common terminology in physics journals. He'd been invited to present findings at conferences in London, Paris, and Tokyo. The National Academy of Sciences had awarded him the William Bowie Medal. The University of Iowa had expanded his research funding and hired 3 additional graduate students for his magnetospheric physics program. But what struck him most was a letter from a Soviet physicist he'd met at a conference in 1956, Dr. Vladimir Vernov, who worked at Moscow State University on cosmic ray research. Vernov wrote that he'd reviewed the Sputnik 2 radiation data after reading Van Allen's published papers and had recognized the saturation pattern in measurements he'd previously dismissed as instrumental error. The Soviet data, Vernov wrote, had contained evidence of the belts but lacked the interpretive framework to recognize it. He congratulated Van Allen not just on the discovery but on the systematic approach that made the discovery possible. The letter was professional, collegial, and completely honest about Soviet failure to interpret their own data. Van Allen appreciated that honesty. Science was supposed to transcend political systems, though he understood it rarely did. The Cold War had militarized space research, classified basic physics, and turned orbital mechanics into strategic intelligence. But occasionally, the scientific method's fundamental requirement that observations must be reproducible and explanations must be falsifiable cut through the propaganda and established truth that both sides had to acknowledge. The Van Allen belts existed regardless of who discovered them or what political system claimed credit. They'd existed for billions of years before humans developed rockets. They would exist for billions of years after human civilization ended. The radiation circling Earth at 2,000 miles altitude had no ideology, no national allegiance, no propaganda value beyond the simple fact that one nation's scientists had been better equipped to measure it. That fact that American instruments had revealed what Soviet instruments had missed was not the same as proving American scientific superiority across all domains. The Soviet Union had brilliant mathematicians, accomplished physicists and engineers capable of building rockets that worked, but the United States had invested differently, built differently, and organized its research infrastructure in ways that produced measurement precision the Soviet system couldn't match. That advantage was structural, not ideological. It came from funding university research programs, encouraging graduate student initiatives, and allowing engineers like Van Allen to spend 8 years refining instruments without immediate pressure to produce operational results. The advantage was real, it was significant, and it shaped the next decade of the space race in ways both obvious and subtle. The Van Allen belts remained invisible, unaffected by their discovery, circling Earth in the same toroidal formations they'd maintained since the planet's magnetic field stabilized billions of years earlier. The protons trapped in the inner belt continued their helical trajectories, spiraling along magnetic field lines between northern and southern polar regions, gaining and losing energy in interactions that followed laws of electromagnetic physics with perfect consistency. The electrons in the outer belt, trapped and released by solar storm injections, maintained average populations that varied with solar activity cycles, producing auroral displays when particles escaped into the upper atmosphere. The belts were a phenomenon, not an achievement. But their discovery was an achievement that revealed capability differences between two systems competing for technological dominance. The United States had demonstrated that its scientific infrastructure could extract knowledge from environments that no human had directly observed, using instruments developed through methodical refinement and deployed with systematic analysis. That demonstration had strategic weight because it proved a capacity for future discoveries in other unmeasured domains. The Soviet Union learned, adapted, and continued launching spacecraft with increasing sophistication. Korolev's team would orbit the first human, Luna 2 would impact the Moon, Venera 4 would enter Venus's atmosphere. Soviet space achievements would continue throughout the 1960s, often achieving firsts that captured international attention. But the Van Allen belt's discovery had established a pattern. American instrumentation would consistently reveal details that Soviet instruments measured but didn't resolve. That pattern would repeat with lunar seismometers, Mars atmospheric analyzers, and deep space communication systems. The discovery taught both superpowers that space was an environment where measurement precision mattered as much as launch capacity. You could reach orbit first, but miss what orbit contained. You could transmit data, but fail to interpret it. You could achieve spectacular firsts while missing fundamental knowledge. And in a competition measured by both symbolic achievement and substantive capability, missing fundamental knowledge meant conceding advantage to opponents who had invested in the instruments and analysis techniques that revealed what you'd overlooked. Van Allen continued his magnetospheric research for the next 3 decades, launching instruments on dozens of spacecraft, refining models of trapped radiation, and training graduate students who went on to design planetary science missions throughout the solar system. He received the National Medal of Science in 1990. He published his final paper on radiation belt dynamics in 2004, at age 90. He died in 2006, having spent 58 years studying the phenomenon that bore his name. The belts remained unmeasured until Explorer 1 carried instruments sensitive enough to reveal them, now mapped with precision by satellites that monitor radiation conditions continuously for spacecraft navigation and astronaut safety. They remain a hazard for orbital operations, a consideration in trajectory planning, and a permanent reminder that Earth's environment extends far beyond the atmosphere's visible boundary into regions that require instrumentation to perceive. The discovery validated the principle that systematic observation, methodically applied, reveals truths that ideology cannot obscure and propaganda cannot alter. The Soviet engineers who laughed at American satellite delays in October 1957 had stopped laughing by May 1958, not because American rockets had become superior, but because American scientists had extracted knowledge from space that Soviet scientists had missed. That knowledge had practical consequences: radiation shielding requirements, trajectory optimization, instrument design specifications, and symbolic weight that shaped international perceptions of technical capability. The Cold War's technological competition would continue for 33 more years, through lunar landings and space station construction, through arms races and détente, through ideological conflict that ended only with the Soviet Union's dissolution in 19... But the pattern established in 1958 persisted. American institutions invested in research infrastructure that produced measurement precision and analytical depth, while Soviet institutions optimized for rapid deployment and spectacular firsts. Both approaches achieved successes. Both approaches suffered failures. But when historians later assessed why one system endured and the other collapsed, the difference in how the two nations approached scientific research, how they funded it, organized it, and valued methodical investigation over immediate propaganda would feature prominently in explanations. The Van Allen belts had always been there. One nation's scientists simply developed the instruments to prove it. If you found this exploration of Cold War technological competition valuable, I'd like to hear your thoughts. What other scientific discoveries during the space race revealed capability gaps between the superpowers? Share your answer in the comments. This channel examines Cold War history through the technical achievements and institutional decisions that shaped superpower competition. If that approach interests you, subscribe for documentaries that prioritize verified facts, systematic analysis, and the human experiences behind historical events. New research every week.